Hello, welcome to a new podcast of Marc and Marc about contamination control monitoring. This is Marc with 25 years of experience of fill finish equipment, and I'm together with.
Hello, I'm Marc with 25 years of contamination control and monitoring. Nice to see you again,
Hello,
Marc.
Marc. Great to see you back.
Yep.
Today we have a topic. We decided to talk about the monitoring inside the depyrogenation tunnel because there's so many questions, especially now with the 1 meter. It's basically impossible to do it in the tunnel. So everyone is asking us lately what to do. I brought up a couple of slides here to see better and to have the people the chance to look at this on YouTube later. And so basically we have points where is the tunnel and what is a tunnel? Why is it important to monitor in the tunnel? Why are we not monitoring in the preheating zone or in the heating zone? If we have several cooling zones, where do we monitor? What does the regulation say about it? So you're the right person to talk about that. Then how to do it? Why are we not monitoring microbial in it? Where to place the ISP probe? What is important to the data which is created? And how can we get away with longer tubing than the 1 meter? So
yeah, it's a question that's been around for quite a long time, Marc. You know, well, we've both been doing this 25 plus years, and monitoring in the tunnel. I kind of maybe answering some of the question here, but you know, monitoring in the tunnel has always been a requirement because it's a grade A space. So people have monitored in all of the tunnel and they go for the hot zone as well, which is kind of, you know, there's a bit of a clue in the name. It's a depyrogenation tunnel. So that heat should kill off any bacteria that's in that hot zone. So why worry about it? Because obviously we're monitoring particles as a real-time view as to the overall contamination of a fixed space, and these are ISO 5 grade A spaces. So yeah, it's been a question that's been around for a long time, and obviously with the advent of more automation, they've become a lot more popular. So we're seeing a lot of questions this last year.
Yes. So coming back to the tunnel, it's in the middle of a typical pharma facility. We have a lot of things we monitor around. Basically, the tunnel is depyrogenating the glassware, which is being washed right before, and then it's moved into the filling line in the isolator. And so it's the major last step between the heat sterilization and the filling machine, where you have a cooling zone, which is not in the clean room, but it is a zone by itself, and it's really critical. If we think back, it feels like yesterday where we talked about you should have a sterilizable cooling zone, where I guess 10 years ago, or maybe still today, not every tunnel had a sterilizing cooling zone. So what happens is you sterilize your glassware and then you send it through an uncontrolled area. And so it only makes sense to have at least particle counting there to see what's going on. We're talking about one particle counter inside the cooling zone at the end of the tunnel. Why not go in the preheating zone or the heating zone, Marc?
Well, and again, I probably just answered this one, Marc. The sterilizer tunnel forms two functions, if we think about it. One of them is transit from a grade C or D area where the washing machine is. So it's a method of transferring glassware into the critical core. And part of that, even if you think of it as a conveyor, that conveyor needs to be continuously sterilized, because anything going into a grade A or anything coming out of a grade A, those conveyors need to be either isolated or continuously sterilized. So here in the sterilizer tunnel, we've got just that. So it's a means of ingress for glassware. But it's also obviously the heat factor kills any residual bacteria and denatures any potential any pyrogens. So the depyrogenation tunnel is causing, two advantages. The reason we don't need to monitor there is, of course, if it's a particulate, it's an inert. And we don't even look for inert 5-micron particles in finished product. We look for 10 and 25 micron particles in finished product. So this isn't a cleaner, if you will. It's a sterilizer. So the particles that are in there are now sterile. So any liquid that you put in there won't, it's kind of like encourage the growth of the inert particles because they're inert. So monitoring in the hot phase, it is a bit academic, really, but it's when the temperatures lower to a potential that'll sustain an organism, that's when, or spore or whatever it might be, that's when we've really got to start thinking about, we should be able to demonstrate that the filtration, the air quality meets a specification. And that's why we focus in on the cooling zone.
Yeah. So I stayed on this picture because this is the end of the cooling zone, and the conveyor, as you said, doesn't go into the filling machine. So it turns around and goes back below and gets sterilized again and goes back out, exactly like you said. And then if we zoom onto the tunnel,
it is the end point then, as you've got it in the flashing blue, the temperature profiles that needs to be monitored, and the regulations call for that to be monitored. So the ISO, sorry, not ISO, the current GMP Annex 1 calls for the airspeed and the air quality within the oven, 0.870, to be monitored and demonstrate that it's within compliance. So how do you demonstrate the air quality relative to risk? And again, we have to lean on risk. Right. And that's using a particle counter dedicated to that last point before it comes into the filling grade A.
Right. So we talked about the preheating zone where it's not necessary, the heating zone where it's not needed and not possible. And then basically for everyone to understand, we have about 300 degrees C in here, so nothing can survive anyway. The whole principle is bringing those bottles through on the conveyor in a slow speed. So they have exposed a certain time, let's say 10 minutes, 300 degrees, and everything is gone after that. So we have a 6 log reduction here. And then sometimes we have big bottles, they take a long time to cool down. So we have several cooling zones, which I tried to show here with the lines. What do you say if we have several cooling zones? Is this considered being like one room each one, or is this like one big zone? Or basically at the end, do we monitor in each zone? And some of those tunnels are 2 meters wide. Do we have to put 2 probes in there?
Again, it really does depend on the design. Personally, if you've got a multi-phase cooling tunnel, you're going to look for that point at which the typical flora and fauna that you have within your facility becomes viable or such that it won't be denatured as a result of the temperature. Obviously, they're going to be stressed. They're not cold, but so something in that typical incubation period, once it drops below about 40 C, that's where we want to be. If in doubt, monitor the final phase and work upstream based upon potential risks. So you've validated those areas, they've been qualified at least twice per year. You have to demonstrate that the filters are installed correctly and that they're working and delivering air quality. So really the high point of risk is, maintaining that differential pressure, and then where it exhausts into the grade A, or where the exhaust from the grade A carousel, where the glassware accumulates, where that air and the cooling tunnel kind of blurs. So that would be my focus. Now, 2 meters wide isokinetic probes. Boy, that's if you put these tunnels are really shallow, i.e. they have a low ceiling. I mean, what would be a typical height for a tunnel?
The exposed area in the middle where the glassware is, maybe a foot.
Yeah, 30 so centimeters. 30 centimeters, 300 millimeters if we want to be precise and German about it, Mark. So yeah, they're about 30 centimeters tall, about a foot tall, like you said. And so to get the sweep of the bend for an isokinetic probe to get, kind of like perfection sampling so that we're not losing particles per se is really hard. So putting in long swept bends for the size of tubing that we're looking at, and then that sweep of the bend leaves the probe right underneath the filter, which will tell you how clean that 1 inch 36 millimeters of area under the filter will be, but with no idea as to the width, at the expanse. So when we look at these, we tend to use like a fluted probe, and that's a single stainless steel probe that stretches across the width of the active tunnel, which could be your full 2 meters if need be. And then from that probe, it then exits into a particle counter. So the holes on the top are kind of aligned with the filter face. So it has to be, the flute openings are facing towards the filter because we're collecting that air at multiple points. Now it's a hybridized sample, which is fine. Nobody says it's the air quality, the overall air quality. So it's a mixed air sample that you take, and you're looking for any change to the baseline quality coming off the total width of the filters. So that's typically how we've approached it, is rather than trying to get a single point of measurement, try to take more of an amalgamated measurement from the total air supply within that small space.
And then we see a certain amount of particles, which most likely we see only small particles. There most likely shouldn't be any bacteria flying around there. So the small particles will show us that there's mechanical problems or something like wearing.
Yeah, there's the age-old relationship between small particles and large particles, and why do we measure 0.5 and 5? It's that 0.5 will demonstrate the cleanliness of the area, and the 5 micron will give you that first indicator that macroparticles exist, and it's those macroparticles that have a higher potential to be a viable risk. And there's a lot of ifs, ors, and buts in that little greater than 5 micron are the 10 to 20 microns, and they're the ones that have been demonstrated to be the free floating viables within clean room air. Now, within clean room air, we're talking about 16 to 20 degrees centigrade, not the 40 degrees that we're talking about even in the cooler end of the cool zone. So it is still under some stress. So the 0.5 monitoring will absolutely give us an indication as to the overall air quality being supplied through the HEPA filters, because that's the only requirement for them. It's that the air be HEPA filtered and that the air quality be monitored to ensure continuity. And that's what we'll be delivering here with those single point fluted measurement. Overall quality gives you a really good management of the risk in that small space.
So coming back to our last show with the ISO 14644-21, now we have a much longer pipe. We have bends and so on. We're losing the big particles. What do you say to that? How do you get away with having this installation horizontal, for example?
Well, and again, let's think about the context around the measurement that we're taking. We're less worried about it being a viable contaminant because of the overall its location within that sterile tunnel. So we want to be able to monitor the quality of air for 0.5 and 5 because that's the requirement. And if we're sampling at 1 CFM through this mixed tube, and we've got a 2-meter probe, and at the end of that 2 meters, it'll have a single sweep that goes down into the particle counter. So the particle counter's quite close to the termination point of the sample probe. You don't want it to be too close, and that's why you can't go into too hot a zone, because otherwise you have to cool the air before it gets into the particle counter. Particle counters can be damaged by hot air. So if you monitor further upstream, anything more than about 35 degrees centigrade is going to damage the particle counter itself. So now you have to add cooling to that sample, and it becomes more of an engineering feat to demonstrate everything's okay. So the 2 meters of tubing is beyond the 1, but it's within the bounds of what ISO 14644 Part 21 is trying to recommend, no more than 2 meters. And even if you have 3 meters, doesn't mean that your data is invalid. 0.5 microns will transit 3 meters quite simply. They're very effectively. You might see 5 or 10% loss in a 3-meter tube at 0.5 micron. Now you're going to see 60, 70% in 3 meters with a 5 micron particle, but it's not 100%. Those 5 microns will get through if they're there in sufficient number. Well, when they're not in sufficient number, they're ones and zeros, and so they're occasional events. So then it becomes, how do you react to the occasional 5 micron event in a baseline of 0.5? And that's what we're trying to identify as demonstration of control over the environment. Much the same as we do anywhere else. It's just a little trickier package to demonstrate it in.
So now my tricky last question is, why are we don't doing active air monitoring in here?
Again, as part of your qualification, you would. So when you have the tunnels in a static phase, i.e. the temperatures are there such that they're not going to denature or overstress microbes, so your biannual qualification of your tunnel, you will be monitoring or demonstrating compliance to your qualification standard. And now that microbial qualification is as a requirement of clean rooms and clean spaces for Annex 1, you have to demonstrate that it meets those requirements at fixed measurements. But what does it do day to day, week to week, month to month? And again, that's a relative unknown, but we're reliant on the data that the overall air quality is giving to us. And it's not that you couldn't do microbial monitoring within the cooling zone. It's just that where the cooling zone exits into the accumulation table, we're monitoring right there. So where the air is being supplied through the grade A air supply and the residence time of the glassware is a little bit longer as it sits on that accumulator table, the chance of risk is elevated. The risk is slightly increased that if one of those particles is a microbe, then it may well fall. It's like throwing ping pong balls at the fair into a sea of bottles. The chances are higher because the bottles are static. And when they're stationary, you may well get a ping pong ball to sit in a bottle, but otherwise it just bounces along the top. And the air shower is designed to wash those smaller particles away. So it's a question of risk, Mark. It's not that it can't be done. It's just that it doesn't add a lot of value to why it's done.
All right, understood. So what else did we miss, Marc? Anything important?
Well, for cooling zones, probably not so much. If we do have, like I said, we have had customers that have asked, I need to monitor in the hot zone, and with the best will in the world, we try and talk them off that ledge. But if they've been picked up as an internal audit item or an external audit item and they need to monitor, then we do have to cool those gases down. And there's 2 primary ways of cooling the gases down. One of them is to use a cooled probe, much like a distillation probe, where we have cold water running around the outside of their inner tube to bring it down. And the other one is by dilution. So you can dilute the sample with a lot of air to bring it down to a manageable temperature. Both of them, if you have a wet tunnel, obviously cooling it's just going to fill your particle counter full of liquid, which we love, as you know. And then the dilution, a single particle, if you've got a 100 to 1 or 1,000 to 1 dilution, a single 5.5 micron particle becomes an ISO 5 nightmare. So everything gets amplified by 35 to put it into cubic meter, and then by 1,000. So a single particle gets amplified 35,000 times. So both of them are real tricky.
You're saying it's possible, technically possible, but not feasible.
But it doesn't add to the value of risk. Yeah, absolutely.
All right. So thank you very much for your time.
Always a pleasure, Mark. Always love chatting, as you know.
If anyone has any more questions, please let us know at pmeasuring.com or call your local salesperson. Thank you, Mark. Take care.
And you, Mark. Bye-bye.
Bye.